So the paper that I wanted to discuss for the finals project is this following paper, Quantized Conductance of Point Contacts in a Two-Dimensional Electron Gas. And even though it's quite an old paper, but I wanted to discuss this because this actually discusses quite a few topics that we learn in this course. For example, we learned in this course about quantized conductance, although mostly in the context of quantum Hall effect. This is separate from quantum Hall effect, so it's interesting in that in its own right. It also uses the Landauer formula for conductance, which is something we learned. And this also discusses a little bit about different conductance through different channels. And interestingly enough, I've actually chosen an experimental paper. So this happens to be the first paper that experimentally showed the quantized conductance and experimentally measured the unit of the quantized conductance, or the conductance quanta, which we have also seen in this course as G naught equal to 2e square over h. So let me start with maybe going through the abstract. So what they do in this work is that they have ballistic point contacts, which means that there is no resistance in the sample itself. It's just ballistic conductance. There's no scattering. And they have a means of defining the width of the point contact. And if you remember that how resistance is related to the width of the point contact, then you'll realize that by means of controlling the width of the point contact, you can actually also control the resistance of the point contact. We will see in detail that how exactly they are controlling that. There is no magnetic field here. So this is not Hall conductance in the traditional sense. So this is quantized conductance, but there's no Hall conductance here. They have a sample of gallium arsenide and aluminum gallium arsenide heterostructure. It's a 2D sample, and they see that the conductance changes in quantized steps of e square over pi h bar, which is the same as 2e square over h. When the width controlled by a gate on top of the heterojunction is varied. So they have seen 16 steps they have observed when they changed the width from 0 to 360 nanometer. And they propose an explanation that is based on the quantized transverse momentum in the point contact region. Let's go to the main body of the paper. So they have a device here where they can realize ballistic transport because the condition that you have for ballistic transport is that the mean free path is much bigger than the length of your sample, which is what they have, because the let me find the numbers here. I think they're actually here. The mean free path that they have is 8.5 micrometer, but the length and width of the object of the sample is in the orders of hundreds of nanometers and micrometer. If we can go to the figure here, actually, yes. So the length is 1 micrometer, which is still smaller than the mean free path here. And the width, even the maximum width is in hundreds of nanometers. So width and length both are less than the mean free path, which guarantees that the conductance that we will see here is going to be ballistic conductance. So the main report in this letter is that it's the first experimental study of the resistance of ballistic point contacts in two-dimensional electron gas of this high mobility sample. The point contacts are defined by electrostatic depletion of this two-dimensional electron gas underneath a gate. We will look into detail of what this means in the experimental section, which is right here. And by doing this, by doing the electrostatic depletion of the electron gas, they can actually control the width of the point contact. And of course, this electrostatic depletion is controlled by the gate voltage. So in turn, the gate voltage is the thing that controls the width of the point contact. So in a system like this, where you have a point contact, the classical expression for conductance is this one that's given in equation 1. So it depends on the charge of the electron, the Fermi wave vector, and the width of the point contact. However, this expression is only valid if these conditions are met. Again, the mean free path has to be much greater than the width of the object, and the Fermi wavelength has to be much smaller than the width. Both of these conditions are satisfied in this setup. And for this sample, which is made up of gallium arsenide and heterostructure of gallium arsenide and aluminum gallium arsenide, the Fermi wavelength is 42 nanometer. This is going to be important later, this number, because it comes in the equation. We will see that. Now, a little bit about the experimental setup. I'm not going to go in too much detail of the experimental setup because I'm not an experimentalist, but the idea of how to control the width of the point contact by changing the gate voltage is actually very crucial. So that part, at least, I want to go through. So they're saying here that using an electron beam lithography, a metal gate is made on top of the heterostructure with an opening of 250 nanometer wide. So let's actually look at the figure simultaneously. So this is the figure that they're describing. So normally when there is no gate voltage, this width is filled with electron gas. But when you have a non-zero gate voltage, what this gate voltage does is that it depletes the electron gas, and thereby making the metal contact point available for conductance to go through. So now it's not the electron gas, but the metal point contact that is the medium through which charges are flowing. And the more you deplete the electron gas, the wider your point contact becomes available for conductance to go through it. Basically, that's my understanding of this. So if you start with this value of gate voltage, then the electron gas underneath the gate is depleted, and the conduction taking place through the point contact only. So that's basically what I was saying. And then, of course, you can change this if you have the means of changing the gate voltage. Then, of course, that would control the amount of depletion of the electron gas, and then the point contact can be made available to be more wide or less wide. Now, we know from basic physics that if you have a very wide point contact, a resistor, then the resistance decreases with width, and that we can actually see here. So we see, for example, they're saying that by a further decrease of the gate voltage, the width of the point contacts can be gradually reduced until they are fully pinched off at minus 2.2. That corresponds to this point here. So here the width is very, very small, or almost vanishing. And for that, we have the highest resistance. But the more wide you make your point contact, which corresponds to this minus 0.6 voltage value right here. So at this value, you have this highest width, this maximum width. And for that, of course, we will have the lowest amount of resistance because it's much more wide now. So that's how the width of the contact point is being controlled by the gate voltage. So that's the setup. So once you set this thing up and you start measuring the things, what they found is that there were plateaus in the resistance, and in total there were 16 plateaus that were observed when they changed the gate voltage from -6 to -2.2, which basically means, in other words, that when you change the width from 0 to the maximum width of 250 nanometer. So if you sort of translate this graph into conductance, because you can just calculate from the resistance, you can just calculate the conductance, then you get this transformed graph in figure 2. And this is much more illustrative, because here you can actually very clearly see that there are plateaus that are just integer values of this e square over pi h bar. This is a very interesting graph, because everywhere you see the plateaus, they are aligning almost perfectly with the integer values right here, 6, 7, and so on and so forth. So that is what they found by doing the measurements. Now, of course, the next part of your research is to be able to explain your findings. Yeah, basically here they give more details that about their measurements, that the average conductance increases almost linearly with gate voltage, which is something we can see here, that yes, they have plateaus here, but if you take the average of this is kind of a linear increase. And this tells you that the relation between the width and the gate voltage is also pretty much linear. And if you have 16 steps, and if your total change of width was from 0 to 360, then you get about 22 nanometer of separation. So as you increase the width of the point contact 22 nanometer, you go to the next step and the next step. And this number will also be useful later. So now let's go into the theoretical part of it, the way that they explained this observation. So what they are assuming here for explaining their findings is that they're assuming that there's a quantized transverse momentum in the contact constriction, which means that at this part, basically at the point contact. So what do you get if you take this assumption, if you take the quantized transverse momentum assumption? Well, first of all, let's just write down the equation of conductance once again. So it's given, the quantum mechanical form of this is given in terms of these quantities, where you have that the n naught is the density of states, and then this is the interesting quantity, because this is the Fermi wave, this is the wave vector. So if you take the quantized transverse momentum assumption, then you can write this average wave vector, the Fermi circle average. So this is the average over the different directions in the Fermi circle, and not average in the sense that you do multiple measurements or take average of, not in that sense. So if you take this Fermi circle average, and at that point, if you assume that the transverse momentum is quantized, another way of saying is that there will be discrete transverse wave vectors like this, ky equal to plus minus n pi over w. Then you can write this average value as this expression in equation 3. And then if you apply this back in equation 2, this is the equation that you get. And you can see that here we have the desired quantity, e square over pi h bar, which is what they found experimentally, that this was the jump in the conductance. And this is, long story short, this is basically, the sum is basically over number of channels, so n equal to 1 to nc number of channels, and your number of channels, generally speaking, will just increase from 1, then 2, and 3, and 4. So that explains that jump completely, this equation 4. So now that we kind of have this theory, have this explanation of the things that we see, let's try to make more sense of it. So if this is the conductance quanta, then what you have is that with the increase of W by an amount of half of the wavelength, half of the Fermi wavelength, you will be adding one extra channel. What does that mean? Well, that means that as you increase the width of your point contact by this amount here, lambda f over 2, you'll be adding one more channel, and then that means that your conductance will increase, will jump by an amount of this, e square over pi h, which is pretty much exactly what they found. So now let's go back to the numbers that I said were important. So here we have lambda f for this system. Lambda f is 42 nanometer. And what they found was that if you increase the width by 22 nanometer, then you see a jump in the conductance amount. And this 22 corresponds almost exactly to 42 divided by 2. So this also makes very good sense. They finished this with another formula, which is the Landauer formula that we learn. So Landauer formula is, as you can see, in equation 5. So there's a curious term here, dnm modulo solid square. This is the transmission coefficient. In other words, this is the probability. This is related to the probability of transmission. Now, for ballistic transport, this is always 1 or 0. It's either 1 or 0. There's no it's either yes or no, right? Because it's ballistic. So then this expression will simply correspond to expression 4, equation 4. So you can also come to the same conclusion from the Landauer formula. So with this expression, so that's pretty much the conclusion of the paper. But I wanted to add one more thing, which is actually related to this expression. So you might think, we might think that, okay, so if this is the conductance quanta, that means that the conductance of quantum object can only be integer multiple of e squared over pi h bar. In fact, I thought like that too, that it's always going to be integer of this value, because that's what, if that's the conductance quanta, then that's how it should be, just like photons. But what I missed is that that is only true for ballistic systems. If you have not a ballistic, but I forgot the dispersive system. Yeah, if you have a diffusive system, I'm sorry. If you have a diffusive system, then these values, these transmission probabilities, are not going to be just 1 or 0. There will be a non-zero probability. So what happens then is that you take a probabilistic account of that, and then your conductance can actually be your conductance can have values that are not integers of e squared over pi h bar. This is also sort of cautiously said in the Wikipedia article too, that note that the conductance quantum does not mean that the conductance of any system must be an integer multiple of G naught. G naught is the thing that we've been looking at, the conductance quanta, 2 e squared over h bar, or e squared over pi h bar, same thing. Instead, it describes the conductance of 2 quantum channels, one channel for spin up and so there's spin indegeneracy. If the probability for transmitting an electron that enters the channel is unity, which is the case for ballistic transport, but if the transmission probability is less than unity, then the conductance of the channel is less than G naught. The total conductance of a system is equal to the sum of the conductances of all the quantum channels that make up the system. So in a case with a diffusive conduction, it's not the case that the conductance will simply be an integer multiple of G naught. In fact, it will depend on the probability of this, and it will be multiplied by that, and it could be pretty much any values. I just wanted to finish this paper with that sort of disclaimer, because I myself had that misunderstanding. So I just wanted to make extra caution about that. So yeah, this is a very special paper in the sense that they were the first ones to experimentally actually find this value of conductance quanta, which we take for granted, and especially when, for example, in one of my research too, when we do the numerical simulations, we always have to use the value of G naught, and it's kind of special to me that this is the paper where this value experimentally was seen for the first time.